yesterday. We took a bunch of data regarding the expression of genes in mice that underwent calorie restriction diets, threw it into the AI system to see, well, which genes are most important for the calorie restriction process, which genes are related to each other in which ways. And we found cool stuff. Like we have this MRPL12, this mitochondrial ribosomal protein, gene 12, comes out as being central to calorie restriction. And the AI figured that out. Statistics couldn't figure it out. People couldn't figure it out. You feed the data into the AI, it churns using some statistical pattern mining machine learning algorithms and figures out new stuff. But then a human has to go and take that and cross-correlate with existing research literature, figure out what the hell it means, figure out what experiments do you want to do in mice to take it to the next level. So with narrow AI programs like this one we wrote in the context of my company, BioMind, they're incredibly helpful tools, but they always leave it to humans to interpret what they've done, integrate things with a wider context, and port things to new domains. So my contention, which certainly is not proved, but it's my conjecture based on my own experience and integration of available knowledge, my contention is that general intelligence at the human level or beyond is not going to come about by kind of incrementally generalizing narrow AI applications, like making a better and better search engine, or a better and better biology data mining engine, or a better and better car driving engine. My view is that to achieve general intelligence, you really got to set out to make it general intelligence, and it probably won't be useful in the very beginning. I mean, I've had 3 children, and none of them were at all useful for a long time. And it's arguable whether any of them are any use right now, actually. They kind of cost a lot of money and cause a lot of trouble. So, I mean, an AGI, from the only example we have, when you start out, is a complete idiot. I mean, if you saw a baby and didn't know it was going to grow up, well, it lies there, goes wide, and makes a mess. I think that AGI is likely to be similar in the beginning. It's not going to know very much. It has to learn an awful lot from scratch, and once it's been educated sufficiently, then it can be quite powerful in a variety of different domains. So I do think the right approach is to create something like an artificial baby. I don't want to overinterpret that. It doesn't have to be like a human baby in any detail. But the point is that it may not have useful functionalities in the beginning. It may have to be taught. Only once it gets to a certain level are there going to be practical applications from it. So just to pursue this a little further, let's say you want to make an AI baby of some sort. How do you do it? Where do you do it? Now, you could make it a purely chatbot type thing, just a textual system. I don't think that's totally infeasible, but I've come to the conclusion it's probably not the best approach. Some folks take a Rodney Brooks type of attitude. You got to make a physical robot. And I think that's great. It's just a big hassle. I mean, I've tinkered around with robots, and you spend all your time dealing with actuator and sensor problems, and maybe it's good if you have a huge budget and a team of roboticists, but I've become attracted to a sort of intermediary option, which is embodiment in virtual worlds, where you still have perception, action, cognition, and social interaction, but you don't have to deal with all the nitty-gritty of moving the robot arm here or there, and the bump sensor broke, and there's too much glare for the camera eye, and so forth. The argument against virtual worlds is that right now virtual worlds don't have the sensory and motoric richness of the real world. I mean, the physics simulations in virtual worlds are not that awesome. The amount of data in virtual worlds is not that much. So to the extent that human-level general intelligence just depends on a huge richness of perception and a huge kind of flexibility of affordances in movements, virtual worlds right now aren't as good as the real world. But I think virtual world technology is improving at a really incredible pace, mostly due to video games being so popular. So I'm fairly optimistic that virtual worlds are going to get better and better, so as to support robust learning for artificial general intelligences. I mean, this is a screenshot from a little virtual world that we made in our own AI project called AGI Sim, which is just based on an open source game engine, Crystal Space. And our AI controls that little guy there. And a human being can control that guy there. And in this screenshot, we were just running the AI through some very basic learning experiments based on the psychological theories of Piaget, where the teacher takes a little bunny and hides it in a box. Then the baby has just got to figure out that the bunny is probably going to be in the same box it was hidden in, which is really simple. Of course, you could program an AI to know that with one line of code in a good programming language, and more in C++, which our system is programmed in. But the point is, a human baby actually doesn't know that objects are permanent. Like, a human baby doesn't know that if I put my cell phone behind my back, it's still there, and it's likely to reemerge somewhere eventually. Somewhere between 6 and 9 months, a human baby figures that out. And so we've done experiments making our AI system figure that out based on embodied experiences as well. And that's taking things down to a really primitive level, of course. We've also done experiments programming in knowledge like that and teaching it more advanced stuff. But you can see that the embodied modality lets you kind of take a very basic, primitive approach to teaching an AI system to understand itself and the world and its surroundings. There's also existing commercial virtual worlds like Second Life, which this is a screenshot from. So there are virtual pets in Second Life, and avatars that people control, as well as avatars that are controlled by simple scripts right now. And Second Life is interesting because it's more rich than a simple simulation world that we built just for testing. I mean, there's millions of subscribers to Second Life. There's a huge kind of virtual topography there with all kinds of stuff going on. So if you put your AI brain inside this dog or inside this guy, and it goes around in Second Life, there are people to interact with it. There are things for it to do. People will chase it around. It can chase people around. People will say stuff to it. It has to figure out how to react. And this is something that we're actively working on that I'll talk about a little later, is using our AI system to control various sorts of agents in Second Life and make use of the richness of that environment. Now, as I said, right now, Second Life physics does exist, but it's fairly primitive. I mean, we've got Newton's laws in there. We've got friction. We don't have fluid mechanics, for example. But I think all that is going to come, because in the PS3, you do have fluid mechanics and so forth. It just hasn't been ported to this domain. So far, all I've done is to say some generalities. I think we should work on artificial general intelligence directly. I think we should do it using virtual embodiment. So I think that the best path forward for the AI field, in terms of the grand old-time goals of the field of really making a thinking machine at the human level or beyond, I think the right thing to do is just to focus on making programs that control embodied agents in virtual worlds and that learn to act like a little baby or a dog and so forth. And once they've mastered those simple behaviors, teach it more and more and more and more stuff until it learns more and more through interacting with people in a shared perception and action context. And that's my best guess for the right general way to approach the AGI problem. Now, of course, that in itself doesn't tell you very much and is not very original either. I mean, people have been talking about that kind of stuff since, well, before I was born, and I'm 40 years old. So there's nothing very new there, although I find it disturbing that so much of the AI field has digressed so far from that to all sorts of other things, because I do think that focusing on this sort of stuff is still the most likely way to get to the end goal. What I'm going to talk about for the rest of the time I have is my own AI architecture, which, according to my best guess, when complete, is likely to be capable of achieving this goal. And certainly in 20, 25 minutes, I wouldn't be able to convince anyone that the architecture really will work as I think I will, even if someone had all relevant knowledge and was emotionally extremely well disposed toward it. It's just an awful lot of detail. And we're developing the Novamente system within a startup company, Novamente LLC, whose business model is focused on controlling virtual agents in Second Life and in massive multiplayer online games and training simulations. So all the description of the system is not published at this point. I mean, we have hundreds of pages of internal documentation. I have published some overview papers of the architecture in various AI conference proceedings at AAAI and IEEE conferences and so forth. So if you're curious to look in a little more depth on the architecture than what I'm going to say in the next 20 minutes, the website novamente.net has a papers page, and you can look at some of the 8-page conference papers, which of course don't tell you anywhere near everything, but they'll help position the approach a little more carefully in your mind. So the Novamente system, how does it work? Well, it is, as I hinted before, an integrative AI architecture. And I started by trying to come up with a holistic system theoretic understanding of how cognition works. So I didn't start with a particular algorithm, knowledge representation. I didn't start from computer science at all. I started from systems theory and cognitive science. Like, what are the parts that a mind has to have? What are the overall high-level dynamics of a mind? How do they interact with each other? What are the emergent structures? Then I took a step back and said, well, how the hell could these things possibly be achieved using tractably implementable computer science algorithms? Not necessarily by imitating the brain, because I don't think we know enough about the brain to use the brain as a detailed guide, but using computer science algorithms integrated in an appropriate way to give rise to the overall structures and dynamics of the mind. And that's the high-level approach that was taken. Right now, we're not done building the thing. There's a detailed design. We're maybe 40 to 50% complete with the implementation and detailed design of it. What we have now is enough to control agents doing some cool things in simulation worlds, but nowhere near where we'd like it to be. So we're progressively building out the system while applying the system for agent control. It's just a list of some of the overview papers, which you can see on the website. So I'm gonna now briefly jump through some of the technical stuff. I'll talk about the knowledge representation, a bit about software architecture. I'm going to end up pretty much glossing over the cognitive processes, which is the most important part, but there's not that much time. And then the high-level emergent structures that are hoped to arise within the system once it's complete. So first, just a bit on the philosophy of mind underlying this whole thing, which I don't think is dramatically original, but I found it useful to formulate it in a kind of precise way. So I view an intelligent system as a system that recognizes patterns in the world and in itself. And key to this, I think, is a reflexive process of a system recognizing patterns in itself, then improving itself based on those patterns. That doesn't entail like deep source code level self-modification necessarily, although it could, but it entails learning and introspective learning, which humans do from a pretty early age and keep doing throughout the course of their lives. And a key part of this is the development of what psychologists and philosophers' mind call the self, or the phenomenal self, the image within the system of the system itself. If an AI can't even recognize itself as a pattern in the world and in its body's interactions with the world, it's not going to have much grounding for any other kind of flexible intelligence. So a lot of the key of getting AGI to emerge, I believe, is getting a system to be good enough at pattern recognition in its world that can recognize what it is in terms of how other things react to it. And that's a lot of what a little baby does in the first year or so of its life. Because when the baby's born, it doesn't know the difference between itself, its mom, and the bed it's lying on. And at a certain point, it gets this idea like, hey, I'm this thing here. My mom is that thing there. This pillow is this thing here. This skin, like, is me, but then when I touch something else, I feel something else. And this basic understanding of what yourself is really critical to ongoing learning and cognition. So as noted before, I consider intelligence as the ability to achieve complex goals in complex environments, and starting to edge toward the technical side of things. One way to look at the achievement of goals is a system recognizing uncertain patterns of the form, well, if I carry out this procedure in this context, I'll achieve this goal. And again, that doesn't say very much, because it's pretty obvious. If you could solve that problem in general, you could do anything. But in terms of generally structuring what the problem is, this is not necessarily the way people would look at things from, say, a neural net or a crisp logic theorem-proving approach to AI. One thing you notice is I place probability theory and uncertainty at the core of the approach, and we'll see that as I launch into the details. So I had a book published last year called The Hidden Pattern, which pretty much just reviews philosophy of mind, going through the whole gamut of issues in cognitive science and philosophy of mind, and trying to largely explain why they're not major problems and how they can be resolved pretty simply in the context of viewing the mind as a big system of patterns that recognizes patterns in the world and itself. So getting toward the nitty-gritty, how does our Novamente system work? Starting off with knowledge representation, and I almost hesitate to use the term knowledge representation because it can be misleading, because I think a lot of what an AGI system has to do is learn how to represent knowledge. So you can almost think of this as a proto-knowledge representation, and then the system has to build its own context-specific knowledge representations on top of that for dealing with different sorts of things. But the low-level kind of proto-knowledge representation of Novamente, it's a graph data structure. You got nodes, you got links, and to look at it really crudely, it's kind of a synthesis of probabilistic semantic networks with attractor neural networks, in the sense that you have nodes and links, and you have weights on the nodes and links that represent probabilistic truth values. You also have weights on the nodes and links that represent what we call attention values, which are sort of like activations or weights in a neural network. So we're putting together attentional type stuff, like in an ANN, with truth value type stuff, like in a probabilistic semantic network. So it's not a neural network in that we're not trying to do low-level brain modeling. It's also not really a pure semantic network, because we're not just representing high-level conceptual knowledge. We can represent procedures to do stuff, percepts that have come in, and so forth, as well as high-level conceptual semantics in the same graph. So the numbers associated with the nodes and links include numbers called attention values. Each node or link has two numbers, a short-term importance and a long-term importance attached to them. And roughly speaking, the short-term importance of a node or link dictates how much attention is paid to it. So the kind of short-term memory, the attentional focus or working memory, is the things with the highest short-term importance. The long-term importance dictates whether something gets kicked out of RAM onto disk or not, basically. And forgetting has been a big focus of our work, because any system that is constantly perceiving a simulation world and generating new ideas generates way too much knowledge to keep in RAM. So you need a fairly sophisticated system to guess what may be relevant in the future. And we also have truth values, probabilistic truth values. We use a particular system where we use a two-component truth value. Each piece of knowledge has a probability and also a number we call a weight of evidence, which tells you how much evidence was gathered to support that probability. And there's a bunch of math underlying there. That actually, it connects with imprecise probability theory interval probabilities, if anyone's looked at that. But in general, pieces of knowledge in the knowledge base are weighted with these 2 valued truth values and the 2 valued attention values. We also have a typology of nodes and links. And the names should be taken with a grain of salt, but we have nodes that represent percepts coming in from the external world, nodes that represent little procedures for doing stuff like move joint at this angle and so forth. And we have nodes that can represent abstract concepts, and basically nodes that are just tokens whose only purpose is to be linked together by links. And then a concept can be viewed as a kind of subgraph or linkage structure among a bunch of nodes and links. So there's a lot of science to this, and actually the knowledge representation scheme is described fairly well in some of the available publications. But the basic idea is that we're using a weighted labeled hypergraph knowledge representation where the weights carry a semantics regarding attention on different time scales and semantics regarding probabilistic truth value within the same network. So this just graphically depicts it. In the same network, we can have nodes representing stuff about joints and actuators being on at a certain time. Nodes with no name at all in English, but they're just meaningful in terms of their relation to other thing. This is a node representing a certain particular instance of raising your arm. This is a node representing the general concept of raising an arm. And all this stuff can be in the same network that's managed in the same way. So you can have links denoting a generic association between things. And I always hate to give these examples because they're a bit misleading, because most nodes in the system wouldn't have any English name. But some of them may correspond to concepts that could be represented in English, and those happen to be the easiest ones to make slides about. But nodes can have a generic association between each other, just meaning that they tend to have been useful at the same time. You can have explicit logic represented, say that just nodes and links representing a predicate relationship. Coffee is often in a coffee cup. That would have to have some probabilistic truth value, but this is really only going to be useful when embedded in some other link structure, because only in some contexts is that true, right? I mean, if it's a coffee bean on a plantation, it's not going to be in a coffee cup. So the really relevant node and link structures, as in any pragmatic system using logic, are going to be big nodes and link structures with a lot of uncertainty associated with them. So people often drink coffee from a coffee cup. Again, we need a whole bunch of these with probabilistic weightings and contextual embeddings to do any use. But nevertheless, logical representation with appropriate probabilistic weighting is a big part of what we're doing. And it's important that that's overlaid with this kind of neural net-like associational representation. And I think you need both of those operating together effectively to adequately represent knowledge for a general intelligence with a graph-type knowledge representation. So software architecture, it's important, but it's kind of standard stuff, so I'll go through it pretty quickly. I mean, we have a big container of nodes and links, which we call the atom space, and a bunch of objects called mind agents that act on it, carrying out different cognitive processes. Then we make it a distributed system, and we can have a whole bunch of those on different machines that all hook together with each other. We can draw a kind of boxes and lines diagram like anyone else can. And I think all these diagrams really kind of look the same, because at this level, cognitive science tells you, yeah, you have perception, you have language, you have actuation control, you have memory, you have goals and feelings. And this looks a lot like the diagrams you'd see from Stan Franklin's LIDA system or Aaron Sloman's cognitive architecture. And not that different from Minsky's Society of Mind or Emotion Machine, if you kind of compress a bunch of Minsky's little boxes into bigger boxes. And I think that it's important to understand things on a high level like this, but ultimately intelligence comes down to what are the dynamic processes going on inside the boxes and how do they interact with each other, rather than this kind of high-level portrayal. A different way of looking at things is as a basic kind of animal-like cycle for for interacting with the world, wherein perceptions come into memory. They elicit feelings in the system, where a feeling can be thought of as a kind of internal sensor. The system has certain goals, some of which you may have supplied, some of which it may have formulated itself by refining the supplied goals. Then it figures out what to do, puts a bunch of procedures in some pool of active procedures, then does something in the world, then perceives it again. And this basic animal interaction type loop, it's just a different way of looking at the same diagram. And the crux of it is in the cognitive processes that occur inside the system, which I'm in no way going to be able to come close to doing justice to in the 5 minutes that I'm now allotting to it. And at a high level, we can look at 3 categories of cognitive processes occurring in the Novamente system. One is what I call global processes. These are cognitive processes that go through everything in the knowledge base and just iterate. An example of that is assigning a long-term importance value. Periodically, you just have to go through and see how important is this thing, upgrade or downgrade the long-term importance, and then kick out of RAM the things that are unimportant. And you just got to cycle through and do that with everything. We have what are called control processes, which are kind of specialized stuff, like executing actions. There's a collection of active procedures, which are called schema, and you just got to go through and execute them. And we use a kind of action selection algorithm similar to Stan Franklin's action selection approach, actually, which is related to Patty May's behavior nets. Then we have the essence of it is what I call focused cognitive processes. And these are cognitive processes that get a small set of nodes and links from the overall table and do stuff on that small set to produce more nodes and links in the table. And this includes logical reasoning. It includes some evolutionary learning type stuff. And that's really where the crux of the thinking is going on. This stuff is kind of mechanical. So if I wanted to summarize in a phrase the philosophy that we've used in crafting the set of cognitive processes, I would put it like this from a computer science perspective. I've become convinced that essentially every cognitive algorithm used within intelligence has exponential complexity. Pretty much all you're doing is making uncontrollable, insane combinatorial explosions one way or another. I mean, if you use evolutionary learning, your population size that you need just blows up when you're trying to learn hard problems. If you're doing logical inference, the process of inference tree pruning and forward and backward chaining just leads you to horrible combinatorial explosions that are hard to prune. So the whole essence of making an AGI design that can work, I believe, is making an integrative system that combines various purpose-specific AI algorithms in such a way that they can cooperate and kind of quell or ameliorate each other's exponential combinatorial explosions rather than making them worse and worse. So I don't think there's any one algorithm that's critical to intelligence. And in fact, I think any one algorithm is just going to blow up in an unacceptable way, which is what you see all throughout the history of AI. The question is whether you can hook different algorithms together so they can kind of calm each other down by decreasing the constant outside the exponential in the exponential time complexity. And since I don't have that much time, I'm going to skip some of the slides and just verbally give what I think is the nicest example of that. So our 2 most critical cognitive processes in Novamente are, on the one hand, an algorithm for probabilistic evolutionary learning, and on the other hand, a probabilistic logic engine. And these are both critical ways of taking nodes and links from the atom table and creating new nodes and links. So the probabilistic logic engine is something I spent several years on, and I think is the best existing integration of kind of theorem-proving logic with quantifiers and variables and all the nice stuff with probability theory, measuring uncertainty in a fairly sophisticated way using imprecise probabilities. So getting logic and probability to work together, it's nice. It lets you do logical theorem proving about stuff like controlling an agent in a world and throwing balls and playing fetch and stuff. On the other hand, when you try to learn complex stuff with it, what happens is that you run the same problem everyone else does, and inference tree pruning and forward and backward chaining inference just becomes unsustainable in terms of the combinatorial explosion. You say, how do you control these inference trees? On the other hand, evolutionary learning, a lot of you are probably familiar with genetic programming. What we're using is something called Moses, which was developed by Novamente co-founder Moshe Lux in his PhD thesis at Washington University in St. Louis. And what Moses does, as compared to genetic programming, is you learn a bunch of little programs to achieve some fitness function. Instead of doing crossover and mutation to generate new programs from the pool of existing ones, you do some probabilistic modeling. You build a probabilistic model of which program trees are good and which program trees aren't. Then you do instance generation from that probabilistic model to generate new program trees. And that works way, way better than genetic programming on a lot of examples. And in Moshe's PhD thesis, he just used it for some basic categorization and symbolic regression. But since that point, within Novamente, we've used it for aging control and a bunch of other stuff. But nevertheless, when you try to scale it up to do learning of large programs with programmatic constructs like loops, recursion, and lists and all this stuff, you still run into a nasty combinatorial explosion. Like the population size just gets really big when you make the tree size too big and the operators at the nodes too advanced. So here we have two really nice algorithms, which, however, considered in themselves, meet the fate of every other algorithm in the history of AI, which is they do well at toy problems, and when you try to scale them up too big, you just run into unsupportable combinatorial explosions. What we're trying to do within our architecture is get these two algorithms to help ameliorate each other's combinatorial explosions. And this happens in a couple ways. So in the Moses probabilistic learning thing, when you have a bunch of program trees satisfying some fitness function, when you're probabilistically making a model of which program trees are good and which ones are bad, what you can do is use the probabilistic logic engine to help with that modeling. You can use the probabilistic logic engine to help do reasoning based on the system's long-term memory and the context in which the system is operating, make inferences about which program trees are good. In that way, if you have an effective probabilistic logic system incorporating long-term memory, it can help a lot with doing the probabilistic modeling within evolutionary learning. On the other hand, within the probabilistic logic engine, when the logic engine hits a dead end, you can then say, well, we have all these options to explore in logical theorem proving. We don't know which one is any good. Well, let's take one of them. Let's take the one that seems most important according to the short-term importance system, and let's use evolutionary learning to see what patterns we can mine about this concept. So if you're trying to prove something and one of the nodes that needs expansion in your backward or forward chaining probabilistic inference tree is a node representing cats, you can then use probabilistic evolutionary learning to mine the knowledge base for interesting patterns about cats. You're then stepping out of the domain of logic. You're doing evolutionary pattern mining to extract relationships, put them back into the knowledge base. Then you re-expand your inference tree using the knowledge gained by evolutionary pattern mining. So you're trying to use evolutionary learning to bust the forward and backward chaining probabilistic inference process out of dead ends, while at the same time trying to use probabilistic logic inference to accelerate evolutionary learning to make its modeling faster. And that's just one example of two cognitive processes and how we're trying to get them to learn from each other, to quell each other's combinatorial explosions. There's other things that have to be drawn in as well. I haven't even gone into attention allocation. How does the system decide which things to pay attention to, which ones not to? We use some actually simulated economic stuff there, modeled on some of Eric Baum's work in Hayek. But I think the key point I wanted to get across there, and I just skipped through all the details on cognitive processes, which I sort of went through verbally, but the key point I want to get across there is, yes, you can integrate a whole bunch of cool learning algorithms, evolutionary learning to learn procedures to achieve stuff in the world, probabilistic logic to reason on existing knowledge and generate new knowledge, unless you can plug these algorithms all into each other to get them to improve each other's performance and stop each other from blowing up combinatorially, you're not going to create an AGI. And this is part of why I think you really have to be working on AGI to build AGI. Because I think that if you're just working on one application, you're going to be able to find some trick to make some one algorithm do what you want just by tweaking it. And in bioinformatics, with that genetics graph I showed before, what we use there is we use Moses, the probabilistic evolutionary learning thing. But because it's a particular domain, we could do some funky parameter tuning and pre-processing to get Moses just to work well in that bioinformatics domain. We don't need all this nasty inter-process integration stuff. But my contention is that for embodied agent control and in a flexible context in a simulated world, you're not going to be able to use tricks to overcome the combinatorial explosions intrinsic in one AI algorithm. You're going to need to use integration in an appropriate architecture to get various algorithms to ameliorate each other's combinatorial explosions. And where does that ultimately lead? Getting back to the high level of things, I'm going to skip slides and just talk more. It's more fun. I'm sick of PowerPoint. So the ultimate crux of this, as I said, is getting the system to recognize its own self as a pattern in the world. And I think we can get there by integrating a whole bunch of these different cognitive algorithms within the architecture that I've outlined. And what I think of as the fundamental dynamic of cognition is what I call a loop of combining followed by explaining, followed by combining, followed by explaining, followed by combining, and so forth. So that we have cognitive processes in the system that take knowledge and then generate new information from that knowledge using logic inference, using probabilistic evolutionary learning and other methods. And then we have cognitive processes that try to explain what's there. And you need an interaction between these two things in the dynamics of your cognitive system. And the crux of this is the ability of the system to understand its own self. So in terms of an agent interacting in a 3D simulation world, what you have is a system that it observes a bunch of things in the world. It observes itself doing things in the world. And then it draws logical conclusions from that, and it recognizes inductive patterns in that. It puts those patterns in its own mind. That then directs its behaviors based on the knowledge it's gathered. Then it has to model itself and say, well, what could I be so as to act the way that I see myself acting? Then it uses reasoning, evolutionary learning, and the other things in its bag of tricks to make a guess of what could I be in order to display these behaviors that I'm displaying. That model, that explanation, feeds back into its own mind and is then used to generate new ideas and new bits of knowledge, which then causes it to act differently. It then has to explain how it acted differently over again, and it just kind of loops around. And the question is, can you get a sophisticated enough collection of cognitive algorithms put together to kind of fuel that loop where the thing studies what it does, tries to explain what it does, that directs its actions, which it then has to re-explain, and you keep going around and around and around. And my hypothesis is that the collection of algorithms and the architecture we've put together in the Novamente system are going to be enough in a simulated world context to allow the system to observe what it's doing in the simulation world, gather data about its own actions, store that data about its own actions in its memory, model what must I be in order to carry out these actions in the simulation world, draw conclusions from that, use those to direct its actions, and keep going around and round. Now, ultimately, I spent some time trying to validate this idea mathematically. I came out with a nice list of 17 mathematical conjectures where, if I could prove them, it would validate that this approach to AI can work. And then I set them aside and put them on my hard drive, and I haven't looked at them since because I decided it would take me 10 years to prove all those things mathematically, and I'd rather just focus on building the system and validating or refuting the hypothesis empirically. And this last slide is just a rundown of what we've done so far. I mean, we built the core system with the atom table, nodes and links, and so forth. We have a logical reasoning engine using probability theory to guide uncertain logical inference. We have the Moses evolutionary learning algorithm, which we've done a lot of simple things with and a handful of complex things. We can enact learned procedures in a simulation world, and we've been working with our own simulation world, but we're going to be rolling out some AI-controlled products in Second Life during the next year, which should be pretty interesting and give more facility for interaction. And we've also done a bit of natural language processing just to allow us to communicate with the system and control what it does. But there certainly is a long path ahead of us to get this thing to work. And as I said in the very beginning, at this high level of abstraction, there's certainly no way I'm going to convince anyone that this is a viable approach in detail, even if I hadn't skipped half the slides due to lack of time. But I do think there's compelling reasons to think that if we're going to achieve artificial general intelligence, we're going to have to work on artificial general intelligence, and that embodied learning is a clearer path there than anything else. Virtual embodiment is easier than physical robotics embodiment. None of the existing paradigms of AI are going to be enough on their own. So we either got to invent something totally wild-ass and new, or take an integrative approach where you put together the best pieces of existing AI paradigms. And if you are going to put together pieces of existing AI paradigms, somehow you have to confront all these combinatorial explosions that exist in every one of them and get the pieces from different paradigms to work together. And that's the framework within which we've been operating. And if you keep an eye on novamente.net for the next couple years, hopefully you'll see progressively more intelligent systems operating in Second Life and game worlds and so forth. We're not going to start out with anything dramatically super intelligent. The idea is to do just like with a human baby, where it starts out a relatively limited but flexible, autonomous, and exploratory system, then gains more and more functionality through learning and interaction. Any questions? Yeah.
Jeff Hawkins and United have very similar goals to yours. What do you think of their system?
Well, I think
Repeat the question.
he said Jeff Hawkins at Numenta has very similar goals, and what do I think of his system? Well, I would say that the goals of our project are not the most unique thing about it, because these goals have been around since at least the 50s, I guess. And the Hawkins approach is more biologically based, at least in principle. Although when you look at what he really has is a kind of pyramidal vision architecture with a kind of hierarchical Bayes net superposed on top of it. And what I feel is that is perhaps a decent qualitative model of visual cortex. And I don't feel it accounts very well for language learning, motor control, mathematical theorem proving, dreaming, all kinds of other aspects of cognition. And in his book, he talks a lot about these other things. I think his philosophy of the memory prediction framework is fine so far as it goes, and you could probably map it into my philosophy of mind as pattern recognition and so forth. But when you look at the detailed stuff he's doing, it's pretty much hierarchical pattern recognition, which in my view doesn't carry you that far toward making a thinking machine. I think that's more along the lines of one particular algorithm, which you can tune to do one particular thing, like recognize patterns in streams of data. you can overcome the combinatorial explosion problem just by domain specialization, rather than by fundamentally coming to grips with it. Yeah.
So you mentioned that it's C++ and scalable, and typically that usually involves that you can run things in parallel and on many machines without too much intercommunication between the parts. I don't know what you put into scalable in your meaning in terms of memory processing and being able to spread the task. But how big does the system need to be in order to achieve this with today's resources?
Well, the honest answer is we don't know how many machines will be needed to achieve like human baby level intelligence or even chipmunk level intelligence, say. I mean, we've done back of the envelope calculations, which suggest that it's not millions or billions of current machines. Like you guys at this company, I'm sure, have more than enough computational resources. We're a small company with a server farm of a few dozen machines, which I think is not going to be enough to make a virtual Ben Goertzel. But really, there's a lot of research to be done to figure out exactly how many machines are going to be needed to achieve a given level of functionality. But in terms of the overall architecture, I mean, what I mean by scalable is, it runs in a distributed network of multiprocessor Linux boxes, and you can add more machines onto it, and the intelligence will increase gracefully rather than the thing getting overwhelmed and crashing. But there's certainly a layer of complexity there, and that if you have a node on this machine and a node on that machine, and the guy on this machine links to the guy on that machine, then it's going to be a lot slower to get a message across from here to there than if they're on one machine. So you have an additional annoying level of complexity of trying to group nodes that cluster together in terms of their internal links on the same machines. And we have code in place that handles that kind of thing. It hasn't been stressed and tuned extensively, and we'd sure be a lot happier to have one massive supercomputer or direct processor-to-processor interconnect fabrics or something. But I don't think hardware is really the bottleneck in getting to AGI, though I think that the bottleneck is getting all the algorithms tuned and interoperating correctly. And then the absolute worst that's going to happen is once we have the thinking machine all designed and working, then you got to wait 5 years for hardware to catch up so that you can run it within your budget. Yeah.
You include ERS FPGA-based learning machines in one of your block diagrams. Are you working with him currently?
I am a good friend of Hugo's, and we've talked a lot about working together. We haven't yet quite gotten to the point of doing anything practical together. What we have discussed doing is the Moses probabilistic evolutionary learning algorithm being run on FPGAs, according to a design of Hugo's, because he's done a bunch of stuff with basically genetic programming. We have neural networks, but it didn't really have to be neural networks. Genetic programming using FPGAs to massively accelerate things. And we've tossed around a bunch of ideas for doing the same thing for the probabilistic evolutionary learning algorithms, but we haven't actually done the work. But this is an area where some advanced hardware design would be useful, actually, because FPGAs can do processing really fast, but they don't have that much onboard RAM. What we really need is an FPGA with a shitload of onboard RAM. Then you could massively speed up the kind of evolutionary learning we use, which would make it a lot cheaper to build a super thinking machine server farm. But we can save that for when we become a Google-scale AI company and can buy hardware companies and subvert them to our purposes. Yeah.
You mentioned there are different kinds of atoms, like moving arms or sensing things.
Right.
How does the system perceive time?
Well, actually, that is a technical detail I did not go into at all. So each thing that comes in perceptually has a timestamp associated with it. And there's actually a special index on each server, which is called the time server, which allows various processes to look up atoms by time interval. So we actually made a separate time management system. And there's a bunch of stuff like that, which is just not gone into here. But an awful lot of attention has gone into various kind of indexes into the knowledge for efficient access, which is a pain in the ass, but seems to be necessary to get things to work in real time. And that's one thing I would say about the virtual embodiment, is needing to control an agent in real time imposes a lot of discipline on you as an AI developer, because things just have to happen fast, and most academic AI approaches just aren't up to real-time control and feasible computational resources. Yeah?
What's the most interesting thing you've seen the system do so far?
Well, it's a good question. The question is, what's the most interesting thing we've seen the system do so far? The thing that interested me most, I would say, is when training the system to play fetch and to play tag, just simple games, the mistakes it makes and the kind of pathological ways of playing fetch and tag that it can come up with are interesting. I mean, we've not tried to get the system to do anything really advanced. All we've done is kind of simple moving around, picking stuff up in the simulation world. So the proto-AGI system has way less interesting behaviors than our specialized bioinformatics systems or something, which have discovered new things about Parkinson's disease and chronic fatigue syndrome and so on. But it's interesting in that if you take a really simple reinforcement learning and try to teach it to play fetch, it doesn't make the same kind of mistakes that this system does when you try to teach it to play fetch. And you can vary the kind of partial reward that you give it for playing fetch or tag correctly, and see how it will misinterpret the partial rewards and which pathologies it will get. They're going to pick up the thing that you threw and kind of coming near you and teasing you, but not quite giving it to you, and so forth. And so you can see the inklings of a personality emerging there. And I'm excited about that in terms of rolling out the system for controlling agents in Second Life. Because once we do that, which should happen around the end of this year, then we'll have a whole bunch of people interacting with it and playing with it, and it should learn a lot from those interactions. All right. Well, thanks for your time. It's been an interesting place to give this talk.
Thank you.